So for problem 1 in the final practice exam, we're given a CDF, and for part A, we're asked to find the expectance of x. So before we get started, I think it's important to determine whether or not this is a continuous or discrete random variable. Because if it is a discrete, you would use the equation for expectance using the summation, where you would use the PMF to calculate the expectance. But if it's continuous, you'd use the integral of x times the PDF. Okay, and we can determine whether or not it's continuous by looking at the CDF. We see here that the CDF function is continuous because between the region 0 and 1, we have this continuous function, x times 2 minus x. And an example of a non-continuous or discrete CDF would be, for instance, if this middle section here was just some number like 0.5, it would jump from 0 to 0.5 to 1. So that's an example of a discrete. But in this case, we have a continuous function. And because our CDF is continuous, we can calculate the expectance using the integral form. Now, before we do that, we need to find the PDF of this function. And if you recall, you can switch between CDF and PDF using integration or differentiation. So if you want the PDF, you can find it by taking the derivative of the CDF. Okay, and just so y'all remember, if you want the CDF, if you had the PDF, you would take the integral from negative infinity to x of the PDF, and you would integrate with you'd use a different variable on the inside because x is up here in the integration bounds. Okay, so now that we know how to find the PDF, let's go ahead and find it. We're going to take the derivative of the CDF. I'm going to rewrite this as 2x minus x squared. And if we take that derivative, you see that we'll get 2 minus 2x, right? So we can write our PDF as two minus 2x, and this is for the region between 0 and 1, and then it's going to be 0 otherwise. Okay, now that we have the PDF, we can go back to our expectation equation to calculate the expectation. Okay, so the expectation of x, the expectance of x, we're going to integrate x times our PDF, which is 2 minus 2x, right? So we'll have 2 minus 2x, and we're going to integrate that with respect to x. And we would integrate between negative infinity and infinity, but our bounds are only defined between 0 and 1, so we can simplify the bounds to 0 and 1. So I'm just going to rewrite this as 2x minus 2x squared dx 0 to 1. Okay, and then we're taking the integral with that with respect to x, right? So we should get x squared. It's going to be 2x squared over 2, but the 2's will cancel. And then you'll have minus 2 over 3x cubed, right? We raise the power by 1, divide by 3. And then we're going to evaluate this from 0 to 1. Okay? So when we do this, if we evaluate at 0, if we evaluate at 1, have 1 minus 2/3. And then if we evaluate at 0, it'll just be 0. So 1 minus 2/3 is 1/3. So this is our answer for part A. Okay. So for part B, we're asked to find the probability that x is less than 0.4. Now there's two ways you can do this. You can either use the PDF or the CDF. If you wish to use the PDF, it's a little bit harder, but the probability that x is less than 0.4, using the PDF, you would just integrate the PDF within the bounds that it's defined, so from 0 to 0.4, and you would integrate the PDF, okay? Now you could do that, but that is a lot less inefficient than using the CDF, because we know that the CDF is defined as the probability that x is less than or equal to x. Okay. Using this knowledge, we can kind of do it in reverse. We know we're looking for the probability that x is less than 0.4. So we can just plug in 0.4 into our CDF. Okay. So what does that mean? We plug in 0.4 into the CDF. So this is going to equal 0.4 times 2 minus 0.4. Okay, and this is from the CDF we had up here. Okay, and so if you plug in those values and multiply them together, you should get 0.64. Okay, so this is a much faster way to do it than using the PDF, if you remember the definition of CDF. And just one thing to note, right? For continuous random variables, right, the probability that x equals some integer is 0, right? So whether or not this x includes 0.4 or not, the calculation will still be the same. You'll still get the same number, okay? All right, so that is problem 1. Let us now move on to problem number 2. So in problem 2, we are given x, y, and z. We're told they're independent, mutually independent random variables. They all have the same mean and variance. So if they have the same mean and variance, we know that the expectation of x equals the expectation of y equals the expectation of z, and they all equal 4. And same thing with the variance. We know the variance of x equals the variance of y, and that equals the variance of z. That all equals 9, okay? So in our first problem here, part A, we're asked to find the variance of x plus 2y plus 3z plus 5, okay? And here, it's important to note that all of this is a linear function, right? We don't have any x squareds or y squareds. And we also know that they're independent. So when calculating the variance, we can simply take the variance of each component of that equation, except for the integer, or sorry, this 5 here. Because it's not associated with any random variable, we don't include it in our calculation. So when when we calculate the variance, we'll have the variance of x plus the variance of 2y plus the variance of 3z. Okay. And the reason we don't include the 5, right, is because if you think about a class of students taking an exam, right, if everyone scores 5 points higher on the exam, right, the average score will definitely go up by 5, but the variance, the spread of data won't change, if that makes sense. If every single student scores 5 points higher, the spread is about the same. It's just that the average goes up by 5. So we don't include the 5 in variance, but we do include it in the expectance. Okay, so now we will use a property of variance. If you're taking the variance of some constant times a variable, you simply take out the constant, square it, and then multiply it by the variance of that variable. Okay, so we will do that for everything here. So the variance of x is still the variance of x. Then we multiply, if we do 2 squared times variance of y plus 3 squared variance of z. Okay, and of course this is 4, this is 9. So we can plug in our variance values. We know variance of x is 9. We do 4 times 9, and then 9 times 9. Okay, so that's 9 plus 36 plus 81, and that gives you 126. Okay. So for part B, we're asked to find the expectance of x squared times y squared. Now, here we need to know, we know that x, y, and z are all independent. Okay. If you have two continuous random variables, if you have two random variables that are independent, then you can use the property of multiplicity here, where the expectance of xy is simply the expectance of x times the expectance of y. Okay. And by extension, you can also think about these as two functions, g of x and g of y, right? So we can extend this further by saying the expectance of g of x times g of y is simply the expectance of g of x times expectance of g of y. But basically what I'm saying here is you can take each component and just multiply their expectances together. So the expectance of x squared times y squared is simply the expectance of x squared times the expectance of y squared. Okay. I just wanted you to see how we got there. And so what we're missing now is what is the expectance of x squared and what is the expectance of y squared? Well, we can do that by using one of the alternative definitions of variance, right? We know that the variance of x is the expectation of x squared minus the expectation of x squared, okay? And we're looking for this part right here, right? This goes into here. So we can rearrange this equation and find that the expectation of x squared is simply the variance of x plus the expectation of x squared. We know the variance of x is 9, and we know the expectation of x is 4, right? That's what we established at the beginning here, and we're going to square that. So we have 9 plus 16, that'll give you 25. Okay. Now, you could go through the same calculation for expectation of x squared, right? We'll know that y squared Expectation of y squared is going to be the same thing, but with y. But we know that the variance of y and the expectation of y is the same as the variance of x and expectation of x. So we'll get the exact same numbers. Okay. So now that we have these, we can plug these back in to our initial expectation equation, right? So we'll have the expectation of x squared times y squared is simply 25 times 25. And that should give you 625. Okay. Now the last problem, part C, asks us to find the covariance of x plus y and x plus z. So for this problem, we have to use some covariance properties. And it's just important to remember, because x, y, and z are all independent, that means the covariance, right, of any single pair will be 0. So what do I mean by that? I mean that the covariance of x, y is 0, the covariance of x, z is 0, and the covariance of y, z is 0. Okay? And this is because x, y, and z are mutually independent. So x is independent from y, x is independent from z, and y is independent from z. So we know these facts already without even reading the question, without reading part C. Okay. So now we want to simplify this, or sorry, break this covariance down a little bit. So we'll be using one of the covariance properties here. In your notes, it's written as the covariance of x and y plus z is the covariance of x, y plus the covariance of x, z. And the way I like to think about this is you're kind of pairing each variable with each other, right? If you remember FOIL from mathematics, it's kind of the same thing, right? So we're pairing x and y together and then x and z together. So if we wanted to do that for this up here, right, we need to pair xx together, xz together, yx together, and yz together, okay? So we can rewrite this as the covariance of xx plus the covariance of xz plus the covariance of yx plus the covariance of yz, okay? Now, another property of covariance is that the covariance of xx, or if you're doing the same variable, is simply the variance of that variable. So in this case, it's just the variance of x, okay? The covariance of xz we established was 0, right? The covariance of yx, or this is also the same thing as the covariance of xy, this is also 0, okay? And finally, the covariance of yz, right? We also established that equals 0. So that means our final answer, right, is simply the variance of x, which is 9, okay? So the covariance of all of this, x plus y and x plus z, is simply 9.